In a recent lecture broadcast on the BBC, British physicist Brian Cox made a statement that made even the most experienced scientists feel uncomfortable. Gravity, as we understand it, may not be a real force. It is a mathematical illusion, a manifestation, not an essence. This was not a metaphysical assumption, but an observation based on decades of theoretical deadlock. Cox was not alone. At universities such as Princeton, Caltech, and Cambridge, a new generation of physicists began to view gravity not as a fundamental force, but as a consequence of something deeper, yet to be understood. This gap is disturbing. After all, if gravity is unreal, if it is merely a shadow of as yet unobserved interactions, then the entire structure of classical physics is built in a mirage. It is like discovering that the ground on which the entire history of science has stood has never been solid. But paradoxically, it is with the help of this illusory Earth that we have reached the moon. Newton's theory of gravity, published in 1657, was sufficient to guide spaceships through a vacuum, accurately predict eclipses, and build skyscrapers that defy the sky. But there is something confusing about it. It is a theory that never explained why something happens, only how. Newton described gravity as an attraction between masses, but he never explained why. What causes it? I do not invent hypotheses, he wrote. I do not invent hypotheses. For Newton, the mystery of gravity was a divine creation. That's all, period. This lack of explanation did not prevent us from moving forward. We flew, we built, we launched probes into space, but at the same time, something remained elusively wrong. An awkwardness, a background noise, like a false note in a perfect symphony. This dissonant note began to really bother us when phenomena such as the orbit of Mercury began to deviate from calculations, or when galaxies receded at an inexplicable speed, or even when experiments showed that time is not the same for everyone, that time is distorted, that clocks slow down, that reality as we understand it is deeply relative. This is where Albert Einstein comes in. In 1945, with the help of special relativity, he destroyed Newton's absolute time. What was once a rigid and universal stage became a malleable fabric. In his view, space and time were not separate entities, but dimensions of the same structure. Space-time and the speed of light became the immutable ruler, the only constant in the universe in motion. But it was not until 1915, with his general theory of relativity, that Einstein completed his rewriting of the cosmos. Gravity, which for Newton was an invisible force between masses, becomes a curvature of space-time caused by the presence of energy. The sun does not attract the Earth. It deforms the space around itself, and the Earth simply follows this curvature. It is a cosmic ballet, not a force. It is geometry, not magic. This elegantly strange theory explained the deviation of Mercury's orbit. It predicted the existence of black holes. It predicted that time would pass more slowly on the surface of the Earth than in orbit. This is what we now correct in our GPS systems. And yet, as revolutionary as it was, it still left uncomfortable questions unanswered. Why does space-time curve? What exactly forms it? If it can be curved, what lies outside it? These questions are not metaphysical, they are technical, they are urgent, especially when technology depends on absolute precision in time. For example, satellites, interplanetary probes, and experiments in particle physics that require milliseconds of time. On a colossal or microscopic scale, any error can mean the difference between discovery and disaster. And this is where the narrative tension intensifies. The deeper we delve into the nature of gravity, the more it eludes us. Today we know that gravity, the weakest of the four fundamental forces, is billions of times weaker than, for example, the electromagnetic force. This defies common sense. This is the gravity we experience every day, the one that keeps us on the ground, holds mountains in place, and pulls oceans together. And yet it pales in comparison to forces at the atomic level. Why does such a weak interaction dominate on the large scale of the universe? And why doesn't it fit in with the other three interactions of the standard model of physics? This is a gaping wound in the heart of modern science. All attempts to unite gravity with quantum mechanics, the so-called theories of quantum gravity, have so far failed. Strings, loops, multiple dimensions, parallel universes. These are all hypotheses in search of evidence. And at the center of this impasse, gravity smiles contemptuously, as if saying, "You still don't understand anything." And just when we thought we were close to understanding, time betrays us again. Because time is not just relative. It is asymmetrical, it has meaning, it flows. But why doesn't fundamental physics give preference to directions? Equations work the same way forward and backward in time. In the microscopic world, reversibility is the rule. And yet our experience is marked by an arrow. The past is fixed, the future is uncertain, and the present slips away like water. Where does this direction come from? What makes the universe follow a timeline rather than wander chaotically along it? The answer may lie in entropy. Things tend to become disordered, but this is also a reflection of our incomplete knowledge. This does not explain the origin of time, it only describes how it behaves. The question remains, what is time? What if time and gravity are closely intertwined in ways we don't yet understand? What if we are only scratching the surface of a reality that is governed by principles completely different from what we imagine? This is not an intellectual game, it is an epistemological emergency. Because while we search for answers, particle accelerators collide atoms at speeds approaching the speed of light. Satellites adjust their clocks so that they don't get out of sync by milliseconds. And scientists in underground laboratories discover particles that barely interact with anything. For example, neutrinos, trying to read the hidden signatures of a universe that stubbornly refuses to reveal itself. Gravity may not be a force after all. Perhaps it is a crack, a symptom, a recurring misreading. And it is this crack that we will now delve into. Time ceased to be universal on May 29, 1919. During a total solar eclipse, two groups of astronomers led by Arthur Eddington positioned themselves at different points on Earth. One gathered in Brazil, the other on the island of Principe off the coast of West Africa, with primitive equipment exposed to heat, humidity, and the instability of photographic plates. They were there to test an idea as absurd as it was bold, that starlight could bend, and he bowed. By recording the position of stars near the solar disk during the eclipse, Eddington confirmed the prediction made 4 years earlier by German physicist Albert Einstein. According to his general theory of relativity, the presence of the sun should warp space and time around it. And starlight passing through this curvature would appear to come from a slightly different location. The world bent along with the light, and Einstein, previously unknown, made headlines. Lights in the dark night confirmed new theory of the universe. But what seemed like mere astronomical curiosity concealed a profound transformation. Time, which had previously been absolute, was no longer the same for everyone. And this changed not only physics, but also how we run the modern world. Today, anyone who uses GPS carries a direct application of the theory of relativity in their pocket. Satellites orbiting the Earth at high speed and altitude are subject to both time dilation, because they are moving fast relative to the Earth, and gravitational time dilation, because they are far from the Earth's gravitational field. Without the relativistic corrections predicted by Einstein and applied by engineers, the navigation system would be off by up to 10 kilometers per day. In other words, without the theory of relativity, we would get lost trying to find our own way. But there is something more inconvenient and less frequently mentioned. Einstein's theories don't just correct our satellites, they reshape our understanding of reality. By acknowledging that time is not fixed, we give up the security that clocks have always given us. What is now, if it is not the same for everyone? Where exactly is the present? And more importantly, if time can slow down or stretch out, is there a boundary between the past and the future? Or is that boundary a convenient fiction? Einstein's famous thought experiment, Einstein's twins, where one of the siblings travels at a speed close to the speed of light and returns younger than the other. This is no longer just a hypothetical curiosity. In 2019, NASA completed a study with astronauts Scott and Mark Kelly, identical twins. Scott spent 340 days on the International Space Station. When he returned, there were minimal but measurable genetic changes in his body, and his biological chronology at the cellular level had been affected. A small difference, yes, but a real, measurable, verifiable relativity in our blood. On a larger scale, This has alarming implications. Space probes, such as Voyager, which have already crossed the boundary of the solar system, are literally moving away from our time. The messages they send come from a past that stretches out. What they capture there, the radiation of stars, pulsars, cosmic winds, is no longer ours in a simultaneous sense. We are connected to a universe that is constantly lagging behind. Every image of a distant galaxy is a record of dead time. Looking at the sky means seeing the past piled up on itself. In practice, we live immersed in a palimpsest of times. This perception is beginning to shake even areas outside of science. For example, in psychology, studies of temporal perception in risky situations show how the brain distorts time under stress. During an accident, a fall, or a threat, time seems to slow down. Is this subjective expansion simply an effect of fear, or is it a neurological reflection of a deeper property of reality that time can actually stretch? In literature, authors such as Jorge Luis Borges and Italo Calvino have explored worlds where time is circular, bifurcated, or frozen. Cinema itself has turned this into a popular pastime. Christopher Nolan's Interstellar. The passage of minutes on a planet near a black hole is equivalent to decades on Earth. The scientific advice for the film was real. Kip Thorne, a physicist and Nobel Prize winner, helped build the narrative based on reliable data. And yes, time really does slow down near a black hole. A stopped clock at the edge of the event horizon means eternity. It's hard to believe that this eternity is not a metaphor. The impact goes beyond that. International banking systems, global communications networks, automated cryptocurrency transactions, stock exchanges. All these structures depend on absolute time. But this time, which seems as solid as the ticking of a wristwatch, is digital juggling. Atomic clocks must be constantly adjusted based on relativistic corrections. World time is an agreement, not a truth. And in times of cyber warfare, even that becomes vulnerable. In 2020, a synchronization failure in the Galileo satellite constellation, a European system competing with GPS, led to a calculation error that nearly jeopardized large-scale military and civilian operations. An emergency correction was required, a microsecond failure. That was enough to partially destroy the entire navigation network. The question arises not how time works, but who controls it. At the heart of this is the growing tension between what time is and what we need it to be. For physics, it is relative. For society, it must be absolute. This contradiction is a new battlefield. In universities, researchers who study the emergence of time are trying to prove that time does not actually exist, that it only appears when there are conscious observers capable of measuring it. This brings the human mind back to the center of the equation and reopens an old wound. Does our perception shape reality or simply record its ruins? If time is an illusion constructed by consciousness, then we are not just victims of the flow, we are its authors. And that changes everything. Our responsibility, our freedom, our understanding of death. Time, this invisible companion of all decisions, may turn out to be nothing more than a collective mirage. And this brings us to an even greater paradox. If time is not absolute, if gravity is not a force, and if space can be curved like a sheet of paper, what can we still call real in the end? It is what we talk about. Not just particles, theories, and experiments, but what lies at the heart of the experience of life, what defines the present. That's what this channel is for. If you've read this far, you know that this is not a documentary curiosity. It is a human dilemma, an existential necessity. If this content resonates with you, subscribe now, like the video, and share this analysis with those who need to rethink what they think they know. The split in reality. GD gravity from Kasvaitsev. In the early 1980s, something strange began to happen in observatories around the world, mapping the rotation of spiral galaxies. Astronomers expected that the speed of stars would slow down as they moved away from the center, just as the speed of a rotating planet slows down as it moves away from the sun. This was a logical prediction based on Newtonian gravity, and it was confirmed in our solar system. But the data showed the opposite. Stars at the edges of galaxies rotated just as fast as those at the centers. There was no slowdown, no dip on the curve. The immediate explanation was elegant but disturbing. There was an invisible form of matter, one that did not emit light, did not absorb radiation, but exerted gravity. This unknown substance was called dark matter. Today, it is believed to make up 85% of the matter in the universe, but it has never been seen, never been detected directly. It has never interacted with any instrument in any measurable way. What to do with an entity that exists only because the equations don't add up? This was the first public failure of gravity. The theory worked well on a local scale, but it fell apart in the face of the cosmos. And when we say it fell apart, we don't mean that rhetorically. Gravity, which had guided us since Galileo, seemed to lose its power at the levels where it should have dominated. So why do we continue to trust it as a framework? The answer was historical. Einstein's general theory of relativity had been thoroughly tested. The eclipse of 1919, the precession of Mercury's perihelion, the gravitational bending of light, the slowing of time, one by one the phenomena coincided. But modern astrophysics began to operate in increasingly distant, less controllable areas. And each discrepancy required the creation of a new invisible entity. Dark matter, dark energy, cosmic inflation. How many patches are needed before someone might consider the possibility that the fabric is faulty? In 1983, Israeli physicist Mordecai Milgram proposed an alternative. If gravity were not constant at all scales, his theory, called modified Newton dynamics, would correct Newton's equation at very low accelerations. According to Milgram, below a certain threshold, gravity would change its behavior, and with that, the rotation curves of galaxies could be explained without dark matter. The proposal was met with skepticism, as are all those who shake the pillars. But Mon passed the test in several dwarf and spiral galaxies. In some predictions, it proved to be more accurate than the standard model with dark matter. This does not mean that Mon is the truth. It simply means that our models are still missing something essential. How many of our scientific beliefs are actually functional approximations? This is not just a theoretical crisis. In 2019, the Gaia Space Telescope showed that the motion of stars in our own galaxy exhibits perturbations that classical gravitational models cannot explain. There are anomalous flows, unusual velocities, and clusters that resist the flow of time. What holds these structures together? Gravity, as we know it, should tear these systems apart over billions of years, but they remain there, intact, defiant. And here comes the second turning point. The universe is expanding faster and faster. This acceleration was discovered in 1998 by observing distant supernovae. A Nobel Prize was awarded, but the main question remains unanswered. What causes this acceleration? They called it dark energy, but that's not an explanation, it's a renaming of ignorance. According to the data, 68% of the universe consists of this energy, but we don't know what it is, where it comes from, or how to detect it directly. It exists because without it, the math doesn't add up. We are reconstructing reality. This pattern repeats itself around absences. As we expand our capabilities, we accumulate invisible entities to support visible theories. Does this mean that the theories are wrong? Not necessarily, but perhaps they are incomplete. Perhaps they are shadows cast by a deeper geometry that we cannot yet see. In 2021, researchers at Fermilab in the US published the results of an experiment with muons, particles similar to electrons but heavier, which indicated abnormal magnetic behavior. The so-called G2 differed slightly from what was predicted by the standard model of particle physics. It was a tiny difference, but statistically significant. Something didn't add up. Some force, some interaction was off the charts. This type of deviation reappears in several areas of modern physics. The signals are weak but repetitive. Small symmetry violations, particles that behave differently than expected, leptons that break the rules. Each anomaly is noise that, individually, could be experimental noise. But when the noise begins to form patterns, the question changes. It is no longer about what is not there, but what we do not see. Physicist Nima Arkani Hamid of the Institute for Advanced Study in Princeton argues that we are approaching a new conceptual revolution. For him, gravity is not a force, but an emergent effect. just as temperature is an emergent property of the chaotic motion of molecules. Gravity, according to this view, would be the result of the geometry of quantum entanglement. Space-time, therefore, would not be the basis of reality. It would be a secondary construct derived from informational relationships. How would you explain the world if space and time were not real? This hypothesis is called emergent gravity, and it appears in many different fields, from black hole physics to string theory, from gravitational holograms to thermodynamic interpretations of the universe. All these fields have one thing in common. Space-time is a useful illusion, but not a fundamental one. Imagine a hologram. You see an object in 3 dimensions, but it is projected onto a 2-dimensional surface. What you see is an effect, not a structure. Apply this idea to space, and what we call gravity would be a distortion in the way information is encoded at the edge of the universe. This may sound like speculation, but it is based on rigorous mathematics published in peer-reviewed journals. The famous holographic principle, proposed by Gerard 't Hooft and Leonard Susskind, was inspired by paradoxes in black holes. It claimed that all the information contained in a volume of space can be described by data on its surface. It's as if the entire universe were a giant hologram. If this is true, then gravity is not something that acts from the inside out as a force, but something that acts from the outside in as a projection. What solid thing remains for us if space itself is a projection? While theoretical physics grapples with these mazes, experiments continue to build tension. The Planck satellite, which has mapped the cosmic microwave background with unprecedented accuracy, has revealed asymmetrical fluctuations that contradict the cosmological principle of homogeneity. The universe does not appear to be perfectly isotropic, challenging not only gravity, but also the concept of symmetry that underlies the laws of physics. We are at a point where each new precision brings us closer to a new abyss. The more clarity we seek, the more instability we find. Science, like any complex system, resonates with its own limits. This is not a sign of failure, but a harbinger of transition. 20th century physics began with ruptures. Quantum mechanics challenged determinism, relativity challenged absolute time. Now in the 21st century, the rupture is different. The very fabric of reality seems about to fall apart, and at the center of it all is still gravity, the collider, and the cat. When reality seeps through on July 4th, 2012, the audience at CERN in Geneva erupted in applause. Scientists in lab coats, data analysts and particle physicists, accustomed to the emotional restraint of research, rose from their seats upon hearing a restrained, almost timid statement. We see strong evidence for the existence of a new particle corresponding to the Higgs boson. It was a technical statement, but the world reacted as if it were the result of a cosmic revelation. After all, it was the last missing piece of the standard model of mathematical structure describing everything that constitutes tangible reality. But in general, the excitement quickly faded into the background. Although the Higgs had been discovered, it raised more questions than it answered. The boson was real, but its mass, decay, and energy did not quite match predictions. Moreover, its existence did not explain the other 95% of the universe, which consists of dark matter and dark energy. It was a partial victory. The press called it the God particle, as if the universe had finally been deciphered. But behind the scenes at CERN, the feeling was different. The discovery did not end an era, it opened a crack. Let's take a step back. The LHC, the world's largest particle accelerator, was built to operate at unprecedented energy levels. Its underground facilities, stretching 27 kilometers between Switzerland and France, are capable of accelerating protons to 99% of the speed of light. When they collide, protons release a tremendous amount of energy, enough to recreate the conditions of the universe in the first trillionths of a second after the Big Bang. But between 2008 and 2012, the tank didn't just discover the Higgs boson, it discovered silence. Thousands of collisions, petabytes of data, billions in investment, and no trace of the particles predicted by theories beyond the standard model. No signs of supersymmetry, no confirmation of dark matter particles, no new forces. It was as if the universe was saying, "You've gone too far with the wrong tools." This absence was considered temporary. Physicists asked for more energy, more luminosity, more time. And indeed, after a break in 2013 and an upgrade, the LHC was restarted with twice the power, and the new phase was named RAN-2. In July 2021, a discovery quietly announced in specialist circles reignited the excitement. Detectors recorded an anomaly in the decay of B quarks, unstable particles that usually transform into electrons and muons with equal probability. Instead, however, asymmetry was observed with more muons than electrons. The deviation was small but consistent. Why is this important? Because according to the standard model of electrons and muons, both leptons should behave identically in high-energy interactions. What was recorded suggests the intervention of a currently unknown force or a new particle of something beyond the current theoretical map. An internal LHCb report from one of the CERN collaborations called the result a possible crack in the universality of leptons. Most people have never heard of this, not because it is unimportant, but because of excessive caution. The scientific community knows that anomalies disappear. This statistical noise is confusing, and the promise of something new before the old has been confirmed can undermine confidence in an entire field. But here's the pause. Why? When theories fail, is it necessary to defend the system first? This is conservative logic. It's understandable, but it's also hidden. A striking example occurred in 2016 when an internal leak from Atlas, another CERN experiment, revealed a statistical spike at 7,150 gigaelectron volts, an unexpected signal that could indicate a new heavy particle. The spike disappeared in subsequent analyses. The hypothesis was ruled out, but it has never been fully explained. How many discoveries are postponed out of caution? How many signals from the universe are ignored because they do not match our expectations? While theory struggles, data continues to accumulate. CERN currently stores more than 400 petabytes of raw data, the equivalent of 100 million high-definition movies. All of this is analyzed by algorithms, neural networks, and filtering protocols that automatically discard 99% of events. Only the most relevant are retained, but who determines what is relevant? In 2022, during an inspection of the Comp Moon solenoid CMS data filtering system, technicians discovered that a number of atypical collisions had been excluded by default. These collisions included extremely short-lived particles with unusual trajectories and slightly unusual energies. The justification was inconsistency with simulated models. The data was deleted. This decision is not scandalous. It is standard procedure, but it also reveals the most subtle flaw in modern science, filtering the universe to fit the model. Think about it. We collide particles at extreme speeds, trying to observe the inexpressible, while believing that our digital filters will not reject what we have never seen. We are searching for the unknown with the tools of the known. It's a paradox, but that's not all. In July 2022, an unprecedented phenomenon was recorded by Earth's magnetic field monitoring systems. For 14 hours, a geomagnetic fault opened a kind of window in the magnetosphere, allowing solar winds to pass through with extraordinary intensity. Polar auroras were observed in regions where they should not have been. NOAA, the U.S. National Oceanic and Atmospheric Administration, published a technical report. The event was classified as a sustained corrotation anomaly. Coincidence. This window coincided with the week of greatest experimental activity at the LHC for the entire year. Some independent publications linked these events. CERN denied any correlation. The data did not indicate a direct cause and effect relationship, but the temporal coincidence, even if accidental, reignited public debate. What is the real range of electromagnetic polygenerators at the LHC? Is there an impact on equipment, networks, and the biosphere? Most of the scientific community confidently answers, no, the system is safe, everything is planned, but there are gaps. Internal reports from 2015 showed that the sudden shutdown of superconducting magnets caused unwanted vibrations in sensors installed hundreds of meters from the facility. Minor vibrations, perhaps, but if there is a local impact, why not consider more subtle systemic effects? This is where physics encounters its own weakness. It requires precise measurements, but operates on the threshold of the incalculable. While the public discusses portals, mandalas, and conspiracies, the real drama unfolds far from the sensational. It lies in data logs that don't add up, in patterns that arise without explanation, in decays that deviate by a millisecond, in a particle that exists for less time than it takes to register. We are trying to encompass the universe with networks built on assumptions. And that's not a failure, it's an admission, because science is not a machine that produces certainties. It is an organism that learns from its mistakes. And right now it stands before its biggest mirror collider. Not because of Higgs's base, but because of everything he didn't explain. Then we descend even lower, like the boundary between what we know and what the universe hides. Where dark matter may be sparse, where emptiness may be full, where gravity may never have existed as we imagined it. Seriousness. Mistakes happen when civilization builds its understanding of the universe on a foundation that may not exist. How do we think? It's a painful question that runs through every page of the report, every LHC collision, every ignored statistical glitch. We have spent more than a century viewing gravity as the basis of reality, from Einstein's geometry to cosmological simulations that predict the heat death of the universe. But now, as data accumulates, it is beginning to look less like an explanation and more like a symptom. For Newton, gravity was an invisible force that bound masses together. For Einstein, it was the curvature of space-time caused by the presence of energy. For today's physicists, it is the absence of one of the four fundamental pillars of nature that has not yet been quantized. All attempts to combine gravity with quantum mechanics have failed. Gravity does not fit into the standard model. It stands outside like a silent god, on whom everything depends but who never speaks. And this absence is not just theoretical, it has consequences. By continuing to rely on a gravitational model that requires invisible entities to function, we cannot conduct research that could completely change our physics. We insist on detecting particles that our own models no longer predict with certainty. We support the work of large laboratories on conceptual maps that break down at the most important points: galaxies, black holes, wormholes, the expansion of the universe. By ignoring the cracks, we risk doing science by inertia, accumulating data that confirms a hypothesis that has already been exhausted. Seeing the universe as a stage when in fact it may be code. Looking for answers with poorly formulated questions. Such hesitation has its price. While we discuss the mass of the base of Higgs or peptone asymmetry, other civilizations, if they exist, may have overcome this barrier millennia ago. Maybe that's why we haven't found them. Perhaps they learned that the universe does not curve, expand, or bend, but vibrates. It generates information. It rewrites itself. And when a species finally understands this, it no longer looks to space for distances, but for logical structures, mathematical meanings, and implicit intelligence. It is possible that gravity is just a derivative, a manifestation of something deeper, a connection between units of information, entropic relationships, holographic projections. This idea underlies some of the most advanced theories in modern physics, such as entangled gravity, holograms, molds, and Hilbert's dynamic spaces. And they all point in one direction. Space is not fundamental, time is not absolute, and gravity is a shadow. This shadow has guided us for centuries, but now it is beginning to betray us. Ignoring this has a civilizational cost. It prevents us from rethinking engineering, energy, and communication. The very perception of life. It chains us to three-dimensionality, to scarcity, to linear causality, to the false idea that the universe is external, inert, separate from us. But understanding this flaw, this noise in gravity, could be the beginning of a new revolution, not only scientific, but also anthological. We are on the threshold of a new paradigm. It is more convenient to deny this transition. This is the path of most people, but facing it head-on is what drives true scientists, visionaries, those who are not satisfied with the obvious. And this is not just an intellectual choice, it is an existential leap. There are two paths before you. Continue to repeat models that do not explain the universe, or enter a zone of turbulence where truths still have no name. If you have reached this point, then you already know which answer will be the most honest. And at this moment, I want to invite you to continue this investigation. Subscribe to the channel right now because what we are doing here is not entertainment. It is resistance to intellectual conformity. Like the video. Comment on your most unpleasant thought. Share this content with those you know who feel that the world is not what it seems. This is the end of the video, but it could be the beginning of something much more disturbing, because deep down, the gravity that holds us back may be the same gravity that calls us to flee.